So the work I developed with Adriana and Maiso is about homogeneity tests for 2x2 contingency tables and a few significance indices. So first we have introduction, then I'll define the test and a few indices. The later three ones I think most of you are familiar with, but the first one, which we call the capital P-value, is one we developed during this work. Then we compare all of them and have discussion and conclusion. So, considering homogeneity hypothesis, especially in contingency tables, it's very common the use of asymptotic results in order to evaluate p-value. And the question which started all this work was if we could construct an exact value for the likelihood ratio test considering this hypothesis. In an attempt to do that, we ended up developing a new kind of index which we call the capital P-value. So, with this new index, we need to evaluate if it's a good alternative for an exact p-value for the likelihood ratio test. And you're going to do that in two different ways. First off, you're going to compare the relationship between the capital P-value with the asymptotic p-value. And also, you're going to, first, there is an asymptotic relationship between e-value and p-value for the likelihood ratio test. Or we want to assure if the same relationship also happens between our capital P-value and the exact e-value. And after evaluating that, we want to know from which sample size are the exact indices closely related to the asymptotic ones. So now the test. So let x and y be two random variables that can be fully represented in table 1. So you are interested in testing if the distributions of x and y are homogeneous with respect to C1 and C2. So considering nx and ny fixed and known, follows directly that x has a binomial distribution nx theta x and y a binomial distribution ny theta y. And the homogeneity hypothesis can be written as theta x equals theta y equals theta. And the likelihood function under this hypothesis is specified by expression 1. So to test this hypothesis with the likelihood ratio test, we have the lambda statistic, which can be simplified by this expression right here. Now the capital P-value. So we started trying to calculate an exact P-value for the likelihood ratio test. In order to do that, we need to find the distribution of the test statistic. So, with that in mind, we wanted to construct an index that was exact and didn't violate the likelihood principle. So, if the main problem was to find the test statistics distribution under the hypothesis. And going for that, we ended up using some ideas from the predictive distribution of x and y. So, we wanted to find a distribution for the test statistic under the hypothesis that did not depend on theta. What we did was, we considered the likelihood function, and the theta we considered it a nuisance parameter. So, we integrated the likelihood over theta in order to eliminate it. Then we got hxy, which is this expression. From that, the probability, to get to a probability, we need a normalization constant. We computed hxy for all possible tables considering nx and ny fixed, find a normalization constant, and ended up with the probability which we call the probability of the table. And since for each table we have a respective test statistic, we automatically have the probability for the probability distribution for the test statistic, which does not depend on theta. And using the cumulative distribution function, we have the capital P-value. So the chi-square test, I guess most of you are already familiar with. We have the test statistic p-square, where O is the observed values, E the expected values, and under mild conditions, it has an asymptotic distribution, chi-square asymptotic distribution, and the p-value follows directly from that. Now the likelihood ratio test, which was our first attempt to construct an exact p-value for it, we have the same test statistic we defined before, and considering mild conditions, minus 2 log the statistic has a chi-square distribution with m minus h degrees of freedom, being m the dimension of the parameter space and h the dimension of the hypothesis. Now to the Bayesian index considered, the e-value. So we're using the full Bayesian significance test. So let pi be the posterior density function of theta and tx the tangent set for the hypothesis. The e-value is calculated by the 1 minus the probability of theta in the tangent set. So assuming theta x and theta y both have prior uniform 0, 1, we have that the posterior density is given by beta distribution. And in a way to calculate the supreme to obtain a tangent set, we have this posterior density, and since we have a lot of integer numbers, it can be simplified by this expression. So then the hypothesis tangent set follows directly from that, and the calculation of the e-value. In order to compute this probability, we use some numerical approximations like MCMC, and we also can obtain an asymptotic e-value. And using the same statistic from the likelihood ratio test, we have -2 a logarithm of lambda follows asymptotically chi-square distribution, but different from the degrees of freedom are different from the likelihood ratio test. Here we have only m degrees of freedom, which is the parametric dimension. So after defining all the indices we're going to use in this work, we're going to have a comparison. So we want to understand the behavior of the capital P value and compare it with other indices. First, since almost all the indices except the chi-square test uses the lambda statistic, we're going to plot the indices against this statistic. So we're going to represent each table by its lambda. And we consider 6 different sample sizes, from 5 to 1,000 and 1,000, and x and y. So first, here we can see that on the horizontal axis, we have the test statistic. On the vertical axis, we have all the indices. We consider all 5 of them. And for example, for 5 and 5, this is not a simulation study. We actually constructed all possible tables considering these sample sizes and plotted all the possible indices here. As sample size increases, we can see that there is a relationship between them that becomes quite evident. This 45-degree line represents the e-values, while this other one, curve one, represents all 3 p-values. The difference between the two of them is because of the construction and the degrees of freedom. While e-value has m degrees of freedom, p-value has m minus h. After looking at bigger sample size, it becomes really clear that all the indices are really similar to each other. But then after looking at them for big sample sizes and knowing what to look for, this relationship, even with small sample sizes like 10 and 10, you can already notice that. So the difference found between both p-values and e-values, it happens because of the difference between degrees of freedom. That is actually an asymptotic relationship from this work. And with that relationship in mind, we want to take a look if the capital P-value and the e-value also show the same relationship. So having the capital P-value on the horizontal axis and the e-value on the vertical one, and the gray line representing the asymptotic relationship, we're going to plot these two indices against each other to see if that happens when sample size increases. Even 5 and 5, we can see that most tables are quite close to the asymptotic line. And as sample size increases, it becomes clear that this relationship also happens in this case. So, the capital P-value does not violate the likelihood principle. And since the distribution of the test statistic does not, and it happens because the sample distribution does not depend on theta. We have also that asymptotic E-values are very similar, and the same thing also happened for all three p-values, even having the capital P-value constructed under a complete different idea. And as the sample size increases, also the capital P-value and the exact T-value drawn towards the asymptotic line. So we consider that the asymptotic relationship between E-value and the likelihood ratio test P-value also happened for exact capital P-value and E-value. Okay, so there is a huge problem with the capital P-value. It takes a lot of computational work. In order to obtain that, for example, for the 100 and 100, we have to compute all possible tables with those marginals. It takes a long time, and we are not really sure if we can calculate that for bigger tables, like 3 times 3, 4 times 3. But since the asymptotic approximation became satisfactory in some unexpected conditions, we can consider that asymptotic indices produce reliable results, even considering small sample sizes. Thank you.